So yeah, I'm here to talk about scaling GraphQL and scaling GraphQL and when I talk about scale, there are two dimensions to scale. There's user scale and then there is organizational scale. Today's talk is about both, but user scale is fairly complex, and my personal journey has been around scaling GraphQL for massive levels of throughputs and requests per second. A little bit about myself. My name is Tushar. That's me and my daughter. And this is the first time I'm here in SF to talk about anything really. And I'm a GraphQL enthusiast, open source contributor. I've worked with programming languages like JavaScript, Rust, Scala, and I'm very passionate about functional programming and developer experience. One of the things I've observed in the last 15 years of engineering is developer experience can have a direct impact on bottom line of an organization. So today's talk is primarily about my journey of the last 8 years that I've spent working on GraphQL. I want to start with my story. In 2016, I joined an organization called Dream11. And it's a fantasy gaming platform, sort of like FanDuel, DraftKings. You make a team, you bet some money, and if the real players sort of win or perform well, you sort of win the contest. That's how it sort of works. And it's a small company, close to 10 engineers, very early stage, and we are considering moving from monolith to microservices. We don't even have an app, right? It's a monolith in the sense, a true monolith, Express.js, sort of a backend with jQuery powered front end. And this is the time when we are considering to move to GraphQL. You might be wondering, it's such a small company, why are you considering GraphQL or moving to microservices? Even at this scale, with such a small team, we had close to 1 million users, registered users on our platform, and 100,000 concurrent users on our platform. That's reasonable scale for you to consider microservices. And it's barely been a year since GraphQL was launched. But we feel like this is an interesting use case and perhaps the best time for us to bet on a technology like this. Our vision is sort of like this, and we achieved this vision over a set of few years, where we have services on the right. We refer to them as upstream, and the clients, which is basically your mobile apps, Android, iOS, and web, and we refer to them as downstream. We have a gateway in the middle and GraphQL between the clients and the gateway. Now, this might be a little interesting because most people end up putting GraphQL between the gateway and the services. We did not do that. And the next set of sections will sort of talk about why did we not do that. Important thing for us to kind of keep in mind is when we were migrating to this microservices architecture, we were thinking about GraphQL as a client abstraction, and not like yet another microservice, right? And that changes the way how services behave or react to requests that are coming from this GraphQL layer. Fast forward 2022, these are some of the numbers we were serving on our platform. There are 500 engineers, 150 microservices. At peak, we were getting 10 million concurrent users on our platform. 10 million people on the platform playing and on the app. And all of this was powered by a very small team working on GraphQL, and it really, really worked well for us. GraphQL actually delivered on its promises. Everything that it said on the website, 6 years, we've tried to optimize GraphQL along the way, but it delivered on those promises. Whether it was type safety, whether it was developer experience, efficiency around querying data, GraphQL did really well. So you might be wondering that GraphQL saved the day. It's a story about how GraphQL kind of made our lives very simple. This whole migration to microservices was awesome, and it's a talk about how well GraphQL did for us, right? But not so much. That's not the story that I'm going to talk about here today. The story that I'm going to talk about is the challenges that we faced. Primarily, the 3 challenges, and the first challenge is performance, right? And when you think about performance, there are a lot of nuances that you want to think about. The first thing is latency and throughput. And when you use GraphQL, the pitch is that it's more efficient in terms of querying data. From that point of view, adding GraphQL actually improved latency and throughput significantly for us. Moving to microservices, we were able to do significant batching, caching, and very efficient data querying via GraphQL. So that promise was delivered. But at the same time, infrastructure is also something that you kind of think about when you think about performance. That it's not something that we were able to kind of get the best out of when we talk about GraphQL. To give you some perspective, we are deploying close to 50,000 cores just for GraphQL. That's a huge amount of infrastructure. Just multiply this by the hourly rate that AWS has per core. You'll kind of get a sense of the amount of money we are burning on just the GraphQL infrastructure. And this is an order of magnitude more than the second highest piece of microservice in our infrastructure. And this is just the EC2 cost, right? This is not databases and all the data stores that we are talking about. Just EC2 cost, which is around this much, right? That's a huge number. And we thought we could do something about it. So some of the things that worked for us was, number one, start micro-optimization. This is primarily a Node.js, JavaScript sort of a stack. We started micro-optimizing, reducing memory locations, inlining, a lot of tricks and tips that are available in changing our GraphQL server, clients, a lot of things, connection pooling, a lot of these things. They're just sort of documented. Search on the internet, you can apply all of them one by one, and you can improve performance quite significantly. The other thing was in infrastructure tuning. What that means is, at this scale, the kind of machine that you use on which you deploy GraphQL matters. Should you use a 4-core machine, 8-core, 32-core, 2-core? What kind of machine do you want to use? What kind of CPU do you want to use? All these things start making a big difference in terms of costs. And we did a lot of experiments around what is the best infrastructure that can give us the maximum throughput. And what we realized was at 4-core, this was the best piece of infrastructure that can give us maximum throughput at the least amount of cost. And a lot of other things around what kind of load balancers are we using, how's the data being routed, what kind of memory allocator, the timing for the GC that we are doing, a lot of such low-level optimizations that's improved performance quite significantly for us. Benchmarking was super critical, and benchmarking, there are two parts to it. Again, there is micro benchmarking, so every line of code we are benchmarking. That's a lot of work. So you're writing 4 or 5 lines of code, some logical operations, we would benchmark, and we would fail the CI if the benchmarks would move away by some threshold, right? But benchmarking is also about load testing. You can test 4 lines of code, you can micro-optimize and improve it, but at scale, how does it work? So you deploy infrastructure at production scale and start benchmarking. And when you have to serve 500 million requests a minute, you don't benchmark at 500 million, you benchmark at 2 billion. At least 4x of that capacity. So that's a huge amount of infrastructure, but investing time, energy, and building all of that was something that we invested, that we actually spent a lot of time in. And the fourth thing was caching on upstream. So the thing with GraphQL is caching is a little tricky. It's tricky not because it's post requests or there's no unique URL. It's tricky because it's an aggregated API. So if you're composing APIs via GraphQL, and you have one API which is extremely volatile and one API which is primarily static, and you compose them together, the net aggregated API is extremely volatile. So you can't really cache. And the second problem is when we migrated to microservices, the services themselves were connected to other services. So the context of caching was primarily understood deeply by the service owners themselves. So you couldn't have a central system which could cache. So what we did was we moved all the caching to the microservices, and that worked out really well for us. All the cache eviction strategy, the TTLs, all of that was within the service, and that scaled really well for us. That being said, the impact of all of these optimization was, we brought down the capacity from 50,000 to around 6,400 cores. That's significant, right? And didn't happen over a week or a month. We took almost a year more than that to kind of get to this number, and it was very slow, very painful, and this system is actually running in production. So you can't just rewrite bits of it. So you have to keep deploying, keep changing, and keep optimizing. So it was quite an expensive affair for us to get this done. And we could only do this because we made it a high priority organization-wide. If the complete organization wasn't aligned around optimizing this layer, we could have never achieved such a significant, almost a 90% reduction in infra cost. Okay, so this is just about performance, right? The second thing was around reliability. A solution like this, or when you think about reliability, there are two parts to it. There's fragility, and then there's resiliency. Fragility is the ability to withstand changes within the system, whereas resiliency is the ability to withstand changes from outside the system. So our solution was fragile as well as not very resilient. And that was because it's a monolithic solution. And when you're spending so much time optimizing, and when you say, okay, I'll not use a map, filter, reduce, instead I'll write 3 for loops and just use a lot of mutable values, the code becomes unmaintainable and becomes very fragile. Somebody will go and refactor and the performance drops by 20%. I just took this code, put it in a function, and the performance has dropped. Why? Because now it's not inlining that piece of code. Why? Because JS optimization is witchcraft. You can't predict. So the code that just works suddenly has a reduced performance and you have no clue. And fragility is not just about performance. Fragility is also about how easy or difficult is it to handle errors and library upgrades and all those kind of things. So it was extremely difficult to kind of manage this piece of code. From a resiliency point of view, the interesting thing is this works like a gateway. So for example, you have an upstream system that starts throwing up errors, and that those errors are not in the path of your hot code, and you've not optimized for it, suddenly the CPU and memory requirements for the GraphQL layer just shoot up by 10x. Because now the upstream is giving you a stack trace, which is huge. You're processing it, you're deserializing it, trying to make sense of it, and you've not optimized for that piece of that path because it was once in perhaps 0.01% of the use cases. Suddenly you're getting outages. You're getting outages because there's a single point of failure, and you're offline, practically offline. So the whole pitch of moving to microservices is that you don't have a single point of failure. Adding GraphQL and not handling these scenarios basically creates a single point of failure. How did we solve this? So first of all, we redefined processes. A lot of time and energy was spent in redefining processes, figuring out coding standards, figuring out how do we do code reviews, all those kind of things. They helped. A lot of documentation. Micro-optimizing cold paths. Now, generally, you are optimizing only the hot paths, things which are very, very frequent. You try to optimize for it so that you can reduce costs. Nobody really optimizes for cold paths, but we had to because those cold paths would take the whole system down. That piece of code which is just executed once in perhaps a day or maybe even lesser, that can take the system down. So we had to optimize for that. We added rate limiting and circuit breaking significantly around our system, and this is why the gateway was a central system rather than gateway. That's why gateway was not in front of GraphQL, but like a hub where all the systems sort of connect to, and that gateway was responsible for rate limiting and circuit breaking. And that gateway is also, because all the services are also connected to other services via the gateway. So maybe the GraphQL is making requests as per what's allowed, as per whatever the thresholds are, but there's another service which is making too many requests upstream to some other service, and that's causing issues in GraphQL. You don't want that. So you need a rate limiting and a circuit breaker sort of a solution in between, and that's what the gateway was doing for us. Query costs. We spend a lot of time, energy kind of evaluating if query costs can be used to build some sort of resiliency. It never worked for us. The problem with query cost analysis was it was too vague. It was statically analyzed, and for example, if I get a query cost of say 1,000, it's hard to translate to real workloads. And because it's hard to translate, it becomes very difficult to predict the impact of a query upstream. Because I'm not incorporating the amount of, is it a batch call? Is that system actually scaled to handle that kind of request? So it became very difficult to kind of make any sense of query costs really for us. And we just went back to traditional approaches of circuit breaking, rate limiting, and the rest of the resiliency, traditional resiliency capabilities that you think about distributed systems. The last thing was maintainability, right? The more we invested in performance and the more we invested in reliability, the worse maintainable the software became. There's so many things that we had to deal with. There were multiple versions of the same library that we had to work with. There were unused nodes, data loaders. Somewhere we were using it correctly, somewhere we were not using them at all. There were unimplemented resolvers. There's schema, which was not connected to any resolver. And there was a lot of code duplication. So it was quite a mess. Nobody in the organization really wanted to contribute to this code base. And even the new joinees who would join in and with great enthusiasm would want to clean this up, they would eventually give up. That's how they would look eventually after a week of refactoring code, and that PR never gets merged, right? So very painful experience. We sat together and sort of analyzed where we were. And if you had to sort of rate performance, reliability, and maintenance, we realized that after a year and a half that we spent optimizing for performance and reliability, we were sort of 2 on 3 in terms of what we expected, both in performance and reliability. But maintenance-wise, we were very poor. It was very hard to build and maintain this piece of software. And a lot of time I get this question, why didn't you consider federation? So our goal was actually to optimize for performance. And what we realized, we did benchmarks with federation, at least back then, the compute requirement would go beyond 30% more. So we have 50,000 cores. It would have taken us 30% more, like 15,000 cores more to kind of work with federation. So that's why we sort of gave up that idea. Okay, so if I had to sort of summarize my learnings of the last 8 years working with GraphQL, I would summarize it as liberty is constraint and constraint liberate. What it really means is, if you set the constraints thoughtfully, your life can become a lot better. Let's take this example. A scenario where you are in a city where there are no rules around driving. There are no lanes, no signals, no penalties, nothing of that sort. Absolutely liberal. Do you think people are going to move? The situation is going to be like this. You're basically stuck. But imagine the opposite. A scenario where you have very precise lanes. 2 separate lanes for incoming and outgoing traffic. Lanes for heavy vehicles, lanes for fast vehicles. This is what comes to my mind when I think about it. So if you build the constraints thoughtfully, you set up some guardrails, life can become a lot easier. And that's very, very applicable to GraphQL. And if you look at the GraphQL spec, it goes in insane level of details around schema and query. So it says this is a type, there are fields, and then fields have types, and then you have meta information, and it tells you about how to define that meta information. And all of this kind of helps you define relationships between entities. And same is true for query. It's very specific about how you want to define a query. You can't mess around with that. And that gives you efficient data fetching capabilities. But about resolvers, it doesn't say anything. It's absolutely liberal. There is no guardrail, nothing. So when it comes to resolvers, it basically says it should just look like the expected response. That's enough. That's good enough for us. So what if we put some thoughtful constraints on the resolvers? After spending so much time, we thought, we at least experimented and hypothesized. If we put some thoughtful constraints on the resolvers, we might be able to improve maintenance of our system. And that's what we did. So we said, okay, let's say you don't write any business logic in this layer. And you just stick to API orchestration logic. So orchestration or API composition, whatever you want to call it. But the idea is don't write business logic, think about composition. And when you start doing this, you realize there are a finite set of primitives that you need. That will be enough. If you compose them together, you can build practically any compositional use case. And it's finite. And when it's finite, what you can do is you don't need handwritten resolvers. You can actually go with a configuration-based approach. And that's a very powerful thing. Because if you think about it, this is not something new. Has anybody heard of Calcite, Apache Calcite here? Okay, so Calcite is a SQL engine. It's a general purpose SQL engine. And what it does is, and it's a very popular SQL engine. It's used by Hive, Druid, and Apache Flink, and a lot of other projects, especially in the distributed system space. You can use the SQL engine to query CSVs or some distributed store or streaming solution, anything of that sort. It just connects. And it does this because it's a general purpose SQL engine. It's generalized. If you take inspiration from SQL, you can actually do very interesting things with GraphQL, a potential for a general purpose GraphQL runtime, right? And that's where I wanted to introduce to you Tailcall. So Tailcall is an open source general purpose GraphQL runtime. It's extremely highly performance, written in Rust, and it allows you to, and I'll tell you how it really works. So the basic idea is, you've defined your schemas over here. This is just standard GraphQL schema. And you just annotate it with the kind of HTTP calls or gRPC calls or whatever you want to call. And that's about it. You start the server by pointing to that config. And you're not writing any resolvers, but you have a production-grade GraphQL runtime ready. It has batching, it has rate limiting, it has all the kind of potential optimizations that you can think of without writing a single line of code. It just does this automatically for you. And it's got first-class support for REST, gRPC, and GraphQL. And it does this by providing tons and tons of operators that can compose well. So these are operators or directors you can apply in your schema, and they all compose. So you can basically create a schema where you can compose a GraphQL request with a gRPC request and a REST API. So you could have 3 upstreams following different protocols, and you can compose them together. And you can go to a degree of composition where you can define your own router. You can design your own router. It could be fusion spec or federation spec or your own custom spec which needs to do some sort of conditional composition. Why not? If you give the right set of primitives, you can actually do a lot more. And these primitives are only possible because we've just put some constraints on the way we define our resolvers. And you can go beyond that. So there are 2 key capabilities that I want to talk about that this generalized runtime called Tailcall gives you. The first one is the ahead of time analyzer. And the advantage of this is you can point it to a configuration, and it can identify all the potential issues upfront. So if you look at it, it says n+1 detected 1. In a conventional GraphQL runtime where you are writing code, unless you make a GraphQL query, you'll not be able to identify if it's an n+1 query. But here, because we can analyze and we've put in constraints around resolvers, it will tell you that there's an n+1 in a particular path, even before you make that query, even before the server starts. So that's fantastic DevX. And you can expand on that, and you can build the schemas in a way where there are no n+1, or you'll be fine with it. It's up to you. It can also identify semantically if the schema is correct. In this case, it says argument ID is a nullable type. And it's saying this because there is perhaps a use case where the IDs cannot be nullable. And it's wrong. And that happens when you define your schema separately and you define your code separately. It's possible that your schema says the field is optional, but your code really wants that field. So that disconnect, it can identify automatically. And again, you're not writing any code for this. This is just using the schema. It's able to identify all of this for you. The second thing is the JIT optimizer. And we've very recently built this just-in-time optimizer which takes the query, creates a plan, and this is a general purpose plan. This is not a plan for just GraphQL. It's a plan that can connect to various data sources and identify the most optimized way to execute it. So it creates the plan, then optimizes the plan, and this optimized plan could be very different from the main plan. It executes the plan and gets the result. And the next time when the query comes in, it executes the optimized plan, right? This significantly improves performance, significantly. order of magnitude higher performance using this approach. If I have to summarize again, right, and we revisit the challenges, of course, you get better performance because of just-in-time. You get better reliability because of ahead-of-time validations. And from a maintenance point of view, now you're not writing any code. You're just working with one schema. And that schema drives your whole GraphQL thought process, right? But the thing that sort of Tailcall compromises on is flexibility. You're not writing code, so it takes away that flexibility. And those constraints around you not being able to write code gives you in return performance, reliability, and maintenance. But it still gets 1 star because for those edge cases where you want to write something custom, it gives you an embedded JavaScript runtime where you can just go ahead and do it. Like if you really care about that custom use case, you can't get over it, just do it in that JS runtime, embedded JS runtime. Okay, so all of this has only been possible because of our awesome open source community. There have been 75 contributors. This project is moving very fast. And all of them have been contributing to this code base for the last 1 year. And almost 80% of the work is done by the community right now. So the thing that makes me the most satisfied and happy about is at least we've been able to build a very, very powerful community of people who want performance out of their GraphQL runtimes. And the last bit today I want to talk about is the key takeaways, right? So first thing is GraphQL needs a lot more innovation in terms of performance. Yes, query planning helps you achieve that, but you can go above and beyond that. Think about different transports that you can use, different kind of serialization, deserialization models you can use. The second thing is handwritten GraphQL is difficult to maintain, right? Think about handwriting a GraphQL router. Nobody does that. You'll use a router that is available in the open source. Same is true for API gateways. It's a finite set of primitives that you need to kind of build a router or a gateway. And that's something you can do with a GraphQL layer also. So if you're moving to microservices and you have APIs, don't handwrite this GraphQL layer. Just use a general purpose GraphQL runtime which can connect to your services and build GraphQL on top of it. And the third thing, I think, which is super critical for library authors, people who are building open source GraphQL, part of the GraphQL ecosystem, I think they should take inspiration from SQL engines. SQL engines have been there for decades, and they've done some really interesting work that you can take inspiration from and really improve the quality of the developer experience that you need to deal with as a consumer of GraphQL APIs, right? All right, so that being said, the last thing I want to talk about, I wanted to announce the GraphQL hackathon. So we're doing a hackathon, and the prize money is $5,000. All you have to do is check out this link, and if you beat the benchmarks, especially the Tailcall benchmarks, if you're faster than Tailcall, you get $5,000. That's about it. Okay? And cool. Yeah, I think that's about it. My name is Tushar. I'm the founder of this company called Tailcall. Prior to that, I was with Dream11. I was heading engineering. I was the VP of engineering there for 6 years. Built this system from scale, from literally zero to scaling. And yeah, happy to connect. Connect with me on GitHub, LinkedIn, Twitter, whatever works for you. All right, thank you. The question is, can we express in some way that there's a batch API that I can use to fix the n+1 problem, right? Yes, you can. So essentially, whenever there's an n+1 problem, you basically have two parts to it. As a dev, I need to know there's an n+1 problem, and then I want to fix it. So the way I know it is the CLI will tell you that there's an n+1 problem in this particular path. And the way I fix it is add that batch API. And the CLI is smart enough to understand that this is a batch API, and it'll just mark that as, it's not an n+1. That's the power you get when you put constraints on resolvers. You can introspect, you can identify if it's a batch versus not a batch API. Yeah? Cool. Any other questions? Yeah, go ahead, please.
So it's
Yeah, we support queries and mutations, not subscriptions just yet, but queries and mutations, yeah, we do.
Any plans on the roadmap for supporting subscriptions? Because with event management, you have the same scale of the cost.
Right.
Tons of events,
Yeah.
and you want to do a no-code type of
We could, like, if you raise an issue, because we have an awesome open source community which is like very excited to do new features. So if you were interested, we could definitely add that feature. Yep. Cool. Sure.
Is there any specific target infrastructure that you stand up on by default, or is it in a container?
Yeah, good question. So it's in Rust. We can deploy it on AWS, GCP, all those kind of things. Serverless, also WebAssembly compatible. So deploy it on Cloudflare or any WASM supported edge platform. Not a problem. Yeah. All right. Thank you so much.